Hi everyone, we're back for one more lesson on trigonometry. This is going to be a lesson about word problems involving trig. Now, earlier in the semester we saw some word problems involving trig, and they were usually about either circles or triangles or angles, or I guess we did have one section where we looked at harmonic motion, and that involved sine waves and cosine waves, and basically, that could be used for sound waves, water waves, things like that. But in this section, we're going to look at word problems using some of the topics we've talked about lately, which was analytic trig. All right, so these are going to be a little different, and let's go ahead and get started. Okay, so word problems involving trig identities and equations. I'll tell you that in this section, we're only going to do a couple of problems, but they take a while. So let's go ahead and write the first one. I think with word problems, the best thing we can do is write a problem and talk through it. So let's see. Two identical tuning forks are struck. One a fraction of a second after the other. The sounds produced are modeled by f1 of t equals c sine omega t, and f2 of t equals c sine omega t plus alpha. So we're using some Greek letters here. The lowercase Greek letter omega looks a little bit like a lowercase w. And then this letter over here is the lowercase Greek letter alpha. Now, I haven't asked any questions yet, but can you imagine this situation? Two tuning forks are struck, and, they're going to make sound waves, and waves can be modeled by periodic functions such as sine. The two sound waves interfere to produce a single sound modeled by f of t equals f1 of t plus f2 of t. So here the idea is that the amount of vibration, basically you strike a tuning fork and the tuning fork vibrates and it vibrates the air around it, and vibrating air is what we call sound waves. So the two sounds basically get added together, the amount of vibration of the air from the first tuning fork and the amount of vibration in the air from the second tuning fork. They're both happening at the same time, so we add them together to get the overall sound. I'm sure somebody who studies physics or acoustics could give a better explanation of that. Anyway, we have two questions about this. First of all, use the addition formula for sine to show that f can be written in the form f of t equals a sine omega t plus b cosine omega t, where a and b are constants that depend on alpha, and c. That's going to be our first part of this question. There's going to be a second part. I think we'll be able to fit the whole question on the screen at least. Second part, suppose c equals 10 and alpha equals pi over 3. Find constants k and phi. This is another Greek letter. Let me just, as we get to Greek letters, I just like to tell you what they are. I'm not going to quiz you on how to pronounce these or anything, but this Greek letter is phi, which can be pronounced either as phi or phi. Either one is fine with us. You know what? I'll go ahead and label some of these in case you're wondering. When I say this is phi or phi, it's usually written like that. This one up here is alpha, and this one is omega. Anyway, find these constants k and phi so that f of t equals k sine omega t plus phi. All right, let me give you a chance just to see all that. I'm going to talk us through the solution because this is going to take a little while. And this is a different kind of word problem. We haven't really done a word problem that uses trig identities. The good thing is that we'll take it one part at a time. You know, let's just focus on part A. And part A tells us to use the addition formula for sine. So it's telling us which trig identity to use. Let's think about what is the goal of part A. Our goal is to show that f can be written in this form. Well, we know what f is. F is f1 plus f2. Here's f1, here's f2. So, you know, we could add these together. And that's f of t. And this problem claims that it can also be rewritten into this form. But it's telling us to use the addition formula. So why don't we get started and see what the addition formula is going to do for us. All right, so solutions. Let's just start by doing what it says. It says use the addition formula. So let's start by writing f of t. How about that? Solutions. All right, part A. F of t. What I'm going to do first is, instead of writing it as f1 plus f2, I'm going to write it as c sine omega t plus c sine of this. Let's start with that. Because really, the problem gave us that this is what f of t is. Okay, with me so far? Now, it tells us to use the addition formula for sine. Let's look at our reference sheet of trig identities. Here it is. Where's the addition formula for sine? That would be this thing. Sine of something plus something equals all this. So sine of an angle plus an angle. That's what this problem is telling us to use. Let's look at what we have here and say, where can we use that? It's going to be here, right? This is sine of something plus something. So this is where the problem wants us to use the addition formula. So we'll do that. First, we have this first term is not changing, and then we have this c out front. That's still there. And now let's apply the addition formula to this, where instead of x and y, we have omega t and alpha. And we'll put those in. So you get sine omega t cosine alpha plus cosine omega t sine alpha. You could add some extra parentheses in there if you want. At this point, let's remember, what are we trying to do? We're trying to show that f of t can be written in this form. Right now we have it in this form. I'm happy that cosine is showing up because it says that we're supposed to be able to write it in terms of sine and cosine. Originally, it only had sine, but now we have sine and cosine, so I think that's a little bit closer. I think we should distribute this c across the parentheses. That's my first idea. Let's write this as 3 separate terms, you know, because there's the c times this, and then c times this. And then I don't need any parentheses. Now, I know what I'm trying to do, right? I'm trying to get it into this form. We have, some of these terms involve sine, some of them involve cosine. How about this? What would it take to get this into this form? Something times sine of omega t plus something times cosine of omega t. The problem claims that it can be written in this form for some capital A and some capital B. What would have to go in these parentheses to make this work? I think that in the first set of parentheses, it's going to be c plus something. How about c plus c cosine? Whoops, I'm trying to write c cosine, and I just wrote like a capital cosine. Let's fix that a little bit. C cosine alpha. How does that look? See what I did? I took the c from this term, and I took c cosine alpha from this term. So these two terms together became this. And then what would have to go in front of this would be c sine alpha. So we did it. We got f of t into the form that the problem told us that it could be written in. So I'm going to say that we found that a should be c plus c cosine alpha. And let b equal c sine alpha. Are these, did we do this? Are a and b constants that depend on alpha and c? Yes, they are. Because look, a is something that depends on alpha and c. B is something that depends on alpha and c. The only variable in this whole thing is t. Right? And a and b do not involve t, so a and b are constants. I'll even just write to summarize, then f of t does equal a sine omega t plus b cosine omega t, as shown above. So this is one of those problems where we kind of knew what the answer was. It told us to do some work to show that f can be written in this form. So we knew that f could be written in this form. I guess we didn't fully know what the answer was because we didn't know what a and b were. That was kind of the part we had to figure out. So you see how this was a word problem that used a trig identity? Luckily, this one told us which identity to use. We need to do part B. I think, let's start this out and see what happens. Part B is giving us c and alpha. So I'm going to write f of t. Let me just show you which version of f of t should we use, because we had a few different versions of it, right? We had this, 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 this. I'm going to use the original form, the first line here, and I'm going to put in what the problem gave us for c, which is 10, and alpha, which is pi over 3. So that's going to look like 10 sine omega t plus 10 sine omega t plus pi over 3. So that's the original form of the function that was given, and I put in c equals 10 and alpha equals pi over 3. I'm going to call this the original form. The original form of f of t that was given. All right. Now, a cool trick that we can do here is we can use what we found in part A. We can say that this also equals, from the form that we found, if we put in, again, put in what it gave us for c and alpha, this is going to look like 10 plus 10 cosine pi over 3 sine omega t plus 10 sine pi over 3 cosine omega t. I'm going to call this the form we found in part A. They have to be equal to each other. The function equals the original function, and it also equals what we found in part A. All right, we want the form f of t equals k sine omega t plus phi, or phi. That's what this part of the problem told us. Here's what I'm going to do. You know, it worked out pretty well in part A, so I'm going to try it again here. I'm going to use the addition formula for sine, because we have sine of something plus something. So let's try to use the addition formula, see if that helps. So sine of omega t cosine phi plus cosine omega t sine phi. And I think that I will, you know what I'll do? I want to distribute the k. But while I'm distributing the k, I'm also going to rewrite this slightly differently. Instead of k times sine of something, cosine of something, I'm going to write it as k cosine phi sine omega t plus k sine phi cosine omega t. So I distributed the k, but I also rearranged these terms a little bit. There's a reason why I did that. I'm going to add some parentheses here. The parentheses that I'm about to write are optional, but I want to show you that what we did is we wrote this as something times sine omega t, and over here is something times cosine omega t. It looks a little bit like the form we had up above, right? Instead of 10 plus 10 cosine pi over 3, we've got k cosine phi. Instead of 10 sine pi over 3, we have k sine phi. All right, let's keep going. We have what I just said out loud. I basically want to write it. The k cosine phi must be equal to 10 plus 10 cosine pi over 3, because they both appear as kind of, you could call them coefficients. They kind of are like a constant in front of the sine term. So we must have k cosine phi equal to 10 plus 10 cosine pi over 3. And what was the other one? K sine of phi equals 10 sine pi over 3. Now, what we're trying to do, just to remind you, is we're trying to find k and phi. What do they equal? We have two equations with two unknowns. Well, actually, the right-hand sides of these equations we can figure out completely. Let's do that. K cosine phi equals 10 plus, you know what cosine of pi over 3 is, right? Think about the unit circle if you need to. It's 1/2. So we get k cosine phi equals 15. let's do something on this other one. So k sine of phi equals sine of pi over 3 is square root of 3 over 2. So we get k sine of phi equals 5 square root of 3. Two equations with two unknowns, and they're a little bit simpler. They're in a simpler form than they were a minute ago. Two equations with two unknowns. So when you have two equations with two unknowns in math, usually you can, hopefully, you can like merge the two equations together in some manner to help solve for the unknowns. Now, it's a lot easier when you have linear equations, right? You've seen that in algebra classes, like two linear equations with two unknowns. Maybe the two unknowns are called x and y, and you do some like substitution where you solve for one in terms of the other. This is a little trickier because they're not linear equations. They have trig. So we need some way of merging these two statements together that in a way that's going to help us solve for the unknowns. There might be more than one way to do this, but I'll tell you an idea that works. Let's divide one equation by the other. Now, this is something that we're allowed to do in math as long as we do left-hand side over left-hand side equals right-hand side over right-hand side. And we could choose which equation do we want to divide by which. Do we want the cosine to be on top, or do we want the sine to be on top? I want the sine to be on top because, look at this. Left-hand side over left-hand side equals right-hand side over right-hand side. All right. I had my choice of which equation to divide by the other. I did this one because I know sine over cosine is tangent. And I think if we did it the other way around, we'd have to work with cotangent. I'd rather work with tangent. What we have here is a k over k. Those cancel. We have a 5 over 15. That simplifies. So get rid of the k over k. And we have sine of phi over cosine of phi equals 5 over 15, puts a 3 on the bottom. All right. And like I said, this is tangent. Tangent of phi equals square root of 3 over 3. We are very close to finding phi. We've got this to one equation with one unknown. Tangent of phi equals this number. So now we could try common angles that we know that involve the square root of 3. We want, sine of something over cosine of something to equal this number. You could draw the unit circle and think about where does the square root of 3 happen. It's usually in the square root of 3 over 2. You could check a couple of those points. The one that's going to work is this one. What is this point here? This is square root of 3 over 2, comma 1/2. Check out what happens if you use, if your sine of phi is 1/2 and your cosine of phi is root 3 over 2. Do you want to check that? Let's check it. This angle, by the way, is phi equals pi over 6, right? Phi equals pi over 6. But what I'm going to check is if I have 1/2 over the square root of 3 over 2, does this get us the number that we want? Well, it's 1 over square root of 3, right? Because the 2's cancel. And then you would multiply this by root 3 over root 3. So yes, this does... That's scratch work there. It does check out. So the angle that gets us to this point is the correct angle. So I'm going to write it here. I'm going to say we found phi equals pi over 6. Now, going back to what this problem said, it said find constants k and phi. We just found one of them. Can we find k now? Yeah, usually in math, if there's two things you're solving for, usually once you find one, finding the other one is not so bad, right? So we have our choice of two equations, and we can choose which one of them do we want to work with. Now that we know what phi is, we can use either one of these equations to find k. So I decided to use k sine phi equals 5 square root of 3. So k is equal to 5 square root of 3 over sine of... I was about to write phi, but let's just actually put in pi over 6 because we know pi over 6 is the value now. In that scratch work above, we already found what sine of pi over 6 is. It's 1/2. What's 5 divided by 1/2? 5 divided by 1/2 is 10. All right, so we found k. We did it. So the solution, we're at the bottom of the page here. The solution, it said the problem said to find k. We found it. It said to find phi, and we found it. So that is the solution. And I'll just say, so what's the point of this? It said find these constants so that f of t could be written in that form. So I'll write it in that form. There. Okay, so this problem took a long time, right? And part B actually took a full sheet of paper for me. So that's why we're only doing a couple of problems in this section. But the idea is to show you that trig identities can be used for things that you might not have thought of. This is a problem about sound waves and, two sounds that are playing at the same time that are interfering with each other. Maybe you've never done that with tuning forks, but you've heard sounds that interfere with each other before, so maybe you can imagine it. And it's kind of interesting that the function that models this interfered sound can be written in so many different forms. There's the original form that the problem gave us. There's the form that we found in part A, and now there's the form that we found in part B. And I actually think out of all of them, this final form that we found in part B is probably the nicest one to work with because it's just one trig function. So that's kind of the idea, is that if you go back to the original problem, f of t was a more complicated function. It had, I'll just show you. It had this, f of t equals something times, all this. There was a sine of something. There was a sine of something else. In the end, we found that that function can be written as just one sine term instead of two sine terms. So pretty cool. Pretty cool. Simplified, simpler. So I've got another problem for us. And it's going to be different. In this lesson, or just the idea of word problems that involve trig identities, every problem is really going to be different, but you use what you know about word problems from other math courses, right? You read the problem carefully. You identify what is given and what is asked for. You assign letters to things if needed. You draw a picture if you think it will help you. All of the usual things that you do for word problems. So this next problem, I'm going to give this to you, and I'm going to ask you to try it on your own. But, you know, you'll try it on your own, see what you can do, and then check back with me. So let's write this all out. There's going to be a part A and a part B for this also. A rectangular beam is to be cut from a cylindrical log of diameter 20 inches. All right, let's move the old problem away. This problem is going to provide us with a picture. Oh, this is actually tough to draw. Give me a minute and let me see if I can draw this right. All right, so it's a cylinder. So we could draw something that kind of looks like a circle. Let's try to give it some perspective. Now, it says a rectangular beam is to be cut out of this wooden log, so let's draw a rectangle. Can you imagine cutting this out from a cylinder? Seems like a lot of wood would go to waste, but maybe that other wood could be used for something else. And this is going to tell us that, well, it told us already, the diameter is 20 inches. So I'm just going to label that. This would be the diameter, wouldn't it? 20 inches. The diameter of the circle, the diameter of the cylinder, is the same as the diagonal of this rectangle. And I didn't ask you any questions yet, so I'm going to first label an angle here. This angle I'm going to label as theta. All right, part A. Show that the area of a cross-section of the beam, the rectangular beam, is modeled by the function A of theta equals 200 sine 2 theta. Now there's a part B, so wait a minute because I have to write that also. In parentheses, I'm going to say where theta is the angle shown. I mean, I think that I didn't really have to write that. I think you know that theta is the theta that's shown in the picture. This is a function, right? A of theta. It's not A times theta. It's A of theta equals this. It's the area function. We're kind of saying that for different angles of theta, you would get a different shaped rectangle, and you would get a different area of a cross-section, because it would be a different rectangle. All right, part B. What is the maximum cross-sectional area of such a beam? What angle, theta, should be used? To get this maximum area. Before you work on this, let me say a couple of things. That's the entire problem. You know, if we were doing this in person, I would ask if anyone had questions about the, like, does everybody understand the question? Like, before you can answer it, you have to understand the question. we're saying that if theta is, I don't know, 20 degrees, or if theta is 30 degrees, you're going to get a different shaped rectangle, right? And that different shaped rectangle is going to have a different area. Part A is asking you to show that that area of the rectangle is 200 sine 2 theta. Interesting. So you might have to use a trig identity or something you know from trig to do part A. And then part B is asking us something that seems kind of practical, because we think, all right, if we're cutting out this rectangular beam out of a cylindrical log, there's a lot of wood that's going to waste. So you might say, what angle can we use that's going to get us the maximum area? And it feels like that would probably involve the least waste from the cylinder. Okay, so now that I've said all of that, I'd like you to pause the video and try this out. So, okay, this is another big problem, isn't it? Well, I think we can use some things we know about triangles. Because I think up there, don't we have a right triangle? So I'm going to draw a picture. Sometimes, even if you're given a picture, sometimes it helps to draw a second one. I'm going to focus in on this right triangle that I see in the diagram, where there's an angle theta, and there's a right angle at this edge. By the way, how do I know that that's a right angle? I know that's a right angle because the problem said that it's a rectangle. Rectangles have to have right angles. And I'm going to label these other side lengths. I'm just going to call them A and B. So, you know how in our lessons about trigonometry of right triangles, we would look at things like, sine of theta, cosine of theta, tangent of theta. Well, what is sine of theta in this picture? I guess it would be b over 20. So that might be helpful. What's cosine of theta? I mean, the issue here is that sine of theta equals b over 20 doesn't really seem that helpful because it's one equation with two unknowns. But let's do this other one here. Cosine of theta is a over 20. Well, that's also one equation with two unknowns. Both of these could be rearranged. B equals 20 sine theta, and this would say A equals 20 cosine theta. So what are we trying to do? We're trying to figure out the area of the rectangle, because a cross-section of a rectangular beam is going to be the area of this rectangle. So what's the area of this rectangle? It's just A times B. Area equals A times B, which, by what we've written above, is 20 sine theta. Oh, actually, well, I guess it doesn't matter if we write AB or BA. Does it? I guess I wrote BA. Same thing. The problem said we want to find the area as a function of theta, and we want it to be 200 sine 2 theta. That's not really what we found here. What we found is 400 sine theta cosine theta. Like, that's the area that we found. It doesn't really look like what the problem said. Do you think we can get what we have into this form? Do you think that those are equal to each other? Yeah, I think so. All right, scratch work. Scratch work time. Do you want to look at our list of trig identities and say which one looks helpful? We need something that's going to somehow relate this expression, which has a sine theta, cosine theta, and it needs to be related to this expression, which has a sine of 2 theta. I think I know which identity we're going to use. You know, where on the sheet do we have something that looks like sine of an angle times cosine of an angle? It's this one here. The double angle formula for sine. This is perfect. This is actually perfect, isn't it? Sine of something, cosine of something equals sine of 2 times. Yeah, that's going to work out perfectly for us. So let's get rid of that and say the double angle formula. You might have been thinking about double angle formula as soon as you saw this sine of 2 theta. Like before we even finished writing the problem, when I saw sine of 2 theta, I'm thinking, okay, double angle formula is one option to rewrite this. Anyway, the formula would, in terms of theta, it would say sine of 2 theta equals 2 sine theta cosine theta. All right, that's my scratch work. So we have, let's apply it. Area equals 400 sine theta cosine theta, which, according to the double angle formula, well, all right, this is 200 times 2, right? So this is 200 sine 2 theta. And that's the end of part A. We kind of knew what the answer was going to be. They told us to show that the area equals this. So in a problem like this, you already know what the area function is supposed to be, and your job is to sort of justify why is that the area function. And it was because of these triangle identities and then combining them, and then the double angle formula. Again, kind of like the previous problem that we did, part B is going to be something that is going to be a little more practical, I think. Because, you know, you'd look at part A and you'd say, all right, well, big deal. So what? The area is this function. What does that do for us? Well, part B is where we get kind of the practical thing. So what is the maximum cross-sectional area of such a beam? What angle theta should be used to get this maximum area? All right, here is my idea. Here's my idea. This is kind of tricky, so don't feel bad if you didn't get all the way through it. But I know that sine of any angle has a max value of 1. No matter what angle you put in, the largest that sine is ever going to be is 1. So sine of 2 theta has max value. What's the max value of sine of 2 theta? It's still 1, right? 2 theta is just some angle. Where on the unit circle does sine equal 1? It's up here. It's sine of pi over 2 that equals 1. So what should theta be? What do you think theta should be here? So let theta equal. It's not pi over 2. It's pi over 4. Why is it pi over 4? Because then when we do sine of 2 theta, we're going to get sine of pi over 2. Yeah, the area formula has sine of 2 theta. So if we put in pi over 4, this is going to work out. So then the area is going to be, well, let's write out this formula. 2 theta. It's going to be 200 times sine of 2 times pi over 4. Let's move the old page. equals 200 times sine of pi over 2, which equals 200. So to answer the question, the max area is 200. And then I look back at the problem and I remember that the diameter was given in inches. So I'm going to say this is inches squared. And this occurs if the angle is pi over 4. Oh, you know what? I guess it didn't really tell us if it wanted the angle in radians or degrees. So I'll say both, 45 degrees. I guess if I didn't really say, do you want radians or degrees, then I guess either one would be accepted. Oh, and you might also look at this and say, like, are there other angles that would also get you the same result? I mean, could we do like a negative angle and wrap around the unit circle, or could we do like an angle that goes around multiple times and winds up at that same point? Well, no, it has to be this angle, because any kind of negative angle or any kind of angle that goes around multiple times is not going to make sense physically in this picture. From the picture, I can tell theta had to be an acute angle. It looked like, right, in order to make a rectangle, like theta would have to be between 0 and 90, somewhere between 0 and 90, and we found that it's actually right in the middle. So part B actually used the observation that we know the maximum value of sine is 1. So as soon as you know the area formula is 200 times sine, you know that the maximum area is going to be 200 times 1. So this actually told us the most efficient way to cut this log. Side note, if you use this angle, what shape are we getting? This gets us a square, doesn't it? If this is 45 degrees, then A and B are going to be equal to each other. That's my picture of a square. It's a little bit messy. But yeah, this actually gets you the maximum area in this problem. So that cylinder that we had that we were cutting, the problem didn't really look like it was a square. But it turns out that if you want the maximum area in a cross section, then the best angle that you could choose would be 45 degrees. And that seems like something kind of practical that we just learned by using trig. And it was pretty cool because we used a combination of some things we knew from lessons about triangles. We also used things we knew, like that the sine of an angle has a maximum value of 1. And somewhere in there we used a double angle formula. So it was a tough problem. The problems we've done in this lesson were long problems and kind of tough. But I wanted to show them to you as examples of problems that use trig identities to do something with the real world. And, in future classes, like if you take calculus, you might see other things that use trig identities that apply to the real world. So I told you in this section we were only going to do a couple of problems because they take a long time. We did 2 problems, but I guess each problem had 2 parts, so it's kind of like we did 4 problems. Yeah, so that's going to be it for word problems right now. We've now seen a bunch of different word problems about trig throughout all the different lessons over the weeks, and hopefully you appreciate that trigonometry has a bunch of different uses. So we're wrapping up our discussion of trigonometry. But there is more to pre-calculus than just trig. So in the upcoming lesson, the next one you see, we're going to jump to a different topic, and we're actually going to move beyond trig for the first time in a long time and talk about some other things. So I'll see you all next time for that, and take care.